Welcome back to the deep dive. This week, we are definitely leaving the incremental tech updates behind because the real story, the one that truly matters coming out of CVS 2026, was a foundational shift for, well, the entire industrial world. We're talking about the debut of the production-ready Atlas humanoid robot from Boston Dynamics and Hyundai. And our mission today is very specific. We're not focused on the backflips. We're unpacking what this leap in hardware and AI actually means for you, the data engineering professional. All the sources point to one thing. This is the arrival of the physical AI flywheel. And this isn't just MLOps on a factory floor. This completely rewrites the data infrastructure playbook for the next decade.
That's it exactly. I mean, the robotics community has been talking about this inflection point for years, and 2026 is the confirmation. But the real story, the one we need to dig into, is the data tsunami that follows. We have to look past the robot itself and understand the pipelines, the infrastructure needed to keep these things learning and working safely 24/7.
Okay, let's start there. Let's unpack the hardware first. This new Atlas is a total evolution. It's the end of a long pivot away from hydraulics. For our audience, for people focused on the data layer, what was the real limitation with hydraulics that this new electric system solves?
Well, hydraulics were just fundamentally incompatible with modern machine learning. They were black boxes.
Black boxes, how?
The shift to all-electric, which really finalized in late 2024, fixed these huge engineering problems. With hydraulics, you had fluid dynamics, seal degradation, variable pressure. It was impossible to get clean, precise data signals. The early models were completely starved of the telemetry they needed to learn effectively.
So the new electric Atlas is basically engineered from the ground up to be a high-fidelity sensor platform.
Precisely. It's a data-generating machine. The sources are really clear on this. The custom actuators give you incredibly precise telemetry across all 56 degrees of freedom.
56. And that's not just position, right?
No, you're getting position, velocity, torque, even temperature. And you're getting it at sub-millisecond resolution. That level of detail is the raw material, the foundation that these large models train on. They're learning real physics, not just guessing from images.
That amount of data is just staggering. But the hardware goes even further into what the sources call beyond human kinematics, specifically joints that can do a full 360-degree rotation. I get the efficiency benefit in a factory, but what does that do to the data itself?
It creates a huge engineering challenge. A good one, but a challenge.
How so?
When you go beyond a normal human range of motion, your state space just explodes in complexity. You can't use simple coordinate systems anymore. The control models have to handle these much more complex, sometimes non-Euclidean data representations in their state vectors. If Atlas swings its arm 360 degrees while holding a part, the model has to navigate all of that without any lag or getting confused. It pushes the real-time inference pipeline to their absolute limit.
And the final piece that makes this a real product, not just a lab project, is the power. The specs are robust, 1.9 meters tall, 90 kilos, 30-kilo payload, IP67 rating, but it's the 4 hours of battery life with the 3-minute hot swappable modules that enables 204/7 operation.
That modular power system is the key. It's the physical piece that makes the physical AI flywheel actually turn. You eliminate downtime, you maximize the time the robot is out there in the real world, generating those terabytes of valuable data. It's what turns a cool demo into a scalable asset.
Okay, so the electric hardware gives us this incredible high-fidelity data stream. The old way of doing things, procedural programming, could never handle that. So that brings us to the brain, VLA and LBM stacks. How are we finally getting the flexibility that old robotics always lacked?
We are seeing the death of procedural programming for any kind of general task. It's over. The work with Google DeepMind and Toyota Research Institute on Vision Language Action Models, or VLAs, is the new paradigm.
A unified neural network, right?
Exactly. Perception, planning, control, it's all handled together contextually. The inputs are rich RGBD images and just plain natural language. So Atlas can inherit this vast world knowledge from language models. You can tell it, clear the debris from the walkway, and it doesn't need a pre-programmed definition for debris. It interprets the command semantically. It uses its general understanding to identify things it's never seen before and figure out how to manipulate them.
And that capability, I mean, it must have sent shockwaves through the research community. The sources say the ICLR 2026 conference saw an 18-fold increase in VLA model submissions. So the research is backing this up. It's the approach that scales.
It is. And on top of that, you have the planning layer, which uses large behavior models, LBMs. These are diffusion transformer architectures, around 450 million parameters. The best analogy is that they treat actions like words in a sentence.
So an LLM predicts the next word.
And the LBM predicts the most likely sequence of actions to complete a task successfully, over a long horizon, not just the next immediate step.
I like that analogy. But if actions are words, how do you even tokenize a continuous motion? The vocabulary from 56 Degrees of Freedom must be almost infinite.
It's definitely more complex than text tokens. It involves discretizing the action space. But the real power of the diffusion transformer is its ability to generate these very smooth, high-quality sequences from noise. It's perfect for modeling human-like motion, especially for complex long-horizon tasks.
And that's what gives it the ability to react.
Yes, through what they call flow matching objectives. The result is real-time reactivity. If a bin lid slams shut while it's reaching, the LBM doesn't crash. It just fluidly adjusts its motion, just like a person would. That's what you absolutely need for it to work in a real unstructured warehouse.
So the robot is smart, it's flexible, and it never sleeps. What does that actually mean for the data professional? I mean, a single atlas generates terabytes of high-dimensional data an hour. You have LiDAR, video, tactile sensors, all that joint telemetry. The first problem isn't training, it's just paying the S3 bill.
Absolutely. The data volume alone makes storage and compression a top-tier infrastructure problem. And this is why you have the digital nervous system, which Hyundai has centralized at their Robot Metaplan Application Center, or RMAC.
And RMAC isn't just a data lake, it's more than that.
It's a curation hub. It's all about validation. It manages two absolutely critical data pipelines that keep the flywheel spinning.
Okay, what are they?
The first is the teleoperation to autonomy pipeline. You have human operators in VR showing Atlas how to do complex tasks. That generates this incredibly valuable multimodal trajectory data.
But it's raw data.
Exactly. It's gold, but it's raw. The key MLO step is that engineers at RMAC have to review, filter, and annotate it to make sure only expert, optimal behavior gets into the training set. You can't have the robot learning the human's bad habits or clumsy mistakes.
That raises a huge question, though. How do you define expert behavior with an algorithm? Aren't you running the risk of filtering out creative, weird, but it works solutions?
That is the core of the curation challenge. It's a huge deal. Expert behavior is usually defined by maximizing efficiency, least power used, fastest time, lowest stress on the joints, rather than just copying the human exactly. It usually involves another high-level reasoning model that checks the physics and efficiency targets before that trajectory data gets approved for training.
Okay, so there's a model checking the model's training data. What's the second pipeline?
The continuous learning loop. When robots are deployed, any edge case, any failure, any moment of uncertainty gets automatically flagged and sent back to RMAC. It's industrial-scale federated learning. You're using the hardest real-world problems from the entire fleet to constantly fine-tune the global model and fight data drift.
But collecting that real-world data is so slow and expensive. The sources mention the RT1 model, 130,000 demonstrations, took 17 months. The flywheel needs to spin faster than that. How does synthetic data fit in?
Synthetic data is the accelerator. It's the force multiplier. They're using platforms like NVIDIA's Isaac Sim and this Groot Dreams blueprint.
Dear Dream.
Yeah. It's a wild concept. From a single image and a language prompt, like robot sorts parts into the red bin, the system can generate a 2D video of what success looks like, a dream.
Mm-hmm.
Then, and this is the critical step, it converts that 2D dream into full 3D action data using an inverse dynamics model.
So it's translating the dream into actual, physically plausible robot movements.
And then it filters that for physical accuracy. The models trained on this mix of real-world failures and filtered synthetic successes are consistently outperforming models trained on real data alone.
And how smart are the reasoning models that filter the synthetic data? Is it another LLM just checking for logic, or is it something more rigorous?
It's both. There's an LLM-like component that checks if the sequence makes semantic sense. Does it logically achieve the goal? But then a formal verification module checks it against the inverse dynamics model to make sure it obeys friction, gravity, all the physical laws. It's a two-step process to keep junk data out.
Right. And none of this AI, none of this real-time adjustment would even be possible without some serious compute at the edge. This brings us to the NVIDIA Jetson Thor module, late 2025 release, and the numbers are just kind of unbelievable. 2070 FP4 TFLOPS, a 7.5x performance leap.
The compute is absolutely essential, and not just for speed, but for safety. Deterministic control is non-negotiable in a factory. The Jetson Thor lets Atlas run its high-level brain, the VLA reasoning, at the same time as its low-level spinal cord, which is the superfast balance and motor control loop.
And they can't interfere with each other.
They can't. And for data engineers, the key tech here is the Blackwell architecture's multi-instance GPU, or MIG. It's hardware-level isolation. You can literally partition the GPU and guarantee a slice of it is only for safety-critical motion control. So the big perception model can't ever steal resources and cause a lag in the safety system.
That's a huge deal for ML ops teams. How do you even monitor that? Does that require totally new observability tools to see inside those isolated partitions?
It does. Your standard telemetry can't see it properly. ML-owns platforms have to integrate with low-level kernel drivers to get the MIG metrics directly. You have to guarantee that safety partition always meets its latency budget. It's a whole new layer of quality of service monitoring at the edge.
Okay, that makes sense. So let's shift to the economics. We know global manufacturing has labor shortages. The ROI seems undeniable. The number everyone quotes is $5.71 per hour for the robot versus $28 per hour for a human warehouse worker in the US.
The economic crossover is here, and that cost includes amortizing the hardware and the power consumption. It's a very compelling business case.
And if, say, 80% of that cost is hardware and data center overhead, what does that mean for the MLOps investment? That has to be a huge part of the calculation.
It's the most strategic part. The ROI only works if the MLOps infrastructure guarantees uptime and rapid model updates. A single robot failure that needs a human to fix it can wipe out the cost savings for a whole shift. So the investment has to be in making your internal data pipelines fast and reliable. We're seeing the blueprint at the Georgia EV plant. Atlas starts with predictable tasks like parts sequencing.
Moving parts to the line in the right order.
Exactly. But by 2030, the plan is for it to do complex assembly with bimanual manipulation. That's the real shift to a software-defined factory.
And the robot as a service model opens this up for smaller companies too.
Vitally important. It gets rid of that massive upfront capital cost. It lets them deploy these robots in brownfield sites, warehouses built for humans with stairs and uneven floors, places old robots could never go.
So the potential is clearly huge, but this widespread adoption, it all hinges on data engineers solving a few really critical factors in the next couple of years. What are the big technical hurdles that could still slow this flywheel down?
Okay, there are three. First is the robustness of generalist policies. The foundation models have to get to true zero-shot or few-shot learning.
Meaning you can't spend weeks retraining it for every new warehouse.
Exactly. It has to be able to do basic tasks right out of the box, just based on its pre-trained knowledge. Second is data quality and curation. The data engineer's job is now data curator. You need automated systems to detect label drift.
Where the definition of a successful task slowly changes over time.
Right, and your old training data becomes poison. You need anomaly detection on the sensor data itself to catch when the robot's behavior starts diverging before it learns a bad habit. And finally, latency and deterministic control. Safety requires sub-10 millisecond control. You can't do that from the cloud. The whole architecture has to be pushed to the network edge using 5G and MEC to guarantee the robot can react faster than any physical danger.
So it all comes back to that physical AI flywheel. Continuous data ingestion, curation, training, deployment, and monitoring, all at a scale that just dwarfs what we think of as MLOps today. The move from tools to teammates has definitely begun.
Without a doubt. The data infrastructure that supports this future is going to be just as critical as the robots themselves. The engineers who master this new architecture, they are the architects of the next industrial revolution.
That is a powerful way to put it. And here is one final provocative thought for you to take away from this deep dive. If synthetic data, filtered by high-level reasoning models for physical perfection, consistently creates better, more optimal robots than raw data from real-world humans, what does that imply about the future definition of expert behavior in this new ecosystem? Thank you for joining us for this deep dive into the Atlas inflection point. We'll see you next time.